Hi all the students. So in my last video I had told you that what is the difference between a propositional statement and a proposition, and how you can convert a propositional statement into a proposition by assigning values to the variables. So up to this point we have seen that a propositional statement, say P of x, can be converted into a proposition by assigning a value to this variable x. So if Px is a propositional statement, then it can be converted into a proposition by assigning a value to the variable x. So here x is assigned the value 4. So if I assume that Px represents that x is greater than 0, so that means in that case P4 represents that 4 is greater than 0, which is true. So that means this propositional statement now has a truth value. It is completely true. So now I can say that this propositional statement is converted into a proposition. So this is how we can convert a propositional statement into a proposition. This is what we have seen. I mean, this is one such method of converting a propositional statement into a proposition. Now in my last video also I told you that the next method or the other way of converting a propositional statement into a proposition is using quantifiers. So that's what we are going to study in today's video. Today we will see how we can convert a propositional statement into a proposition using quantifiers. So we will discuss two most widely used quantifiers, which is the universal quantifier which is denoted by the symbol inverted A, and it is read as for all. And the other quantifier is the existential quantifier. The symbol for the existential quantifier is this, and it is read as there exists. So this is the symbol for the universal quantifier, and this is the symbol for the existential quantifier. Now the rule here is that using a quantifier, if you are able to prove that a certain propositional statement is true, that means the propositional statement is having the truth value true. Here we have to keep in mind that we are not just concerned about a fixed truth value. By fixed truth value, I mean it can either be completely true or it can be completely false. Like when I assign a value to the variable and then convert it into a proposition from a propositional statement. In that case, I am only concerned about a fixed truth value. That means it can either be completely true or it can be completely false. But when we convert propositional statements into propositions using quantifiers, in that case, my concern is not just a fixed truth value, but a true truth value. That means that this proposition statement, that means for a quantifier, if the proposition has a truth value true, only then it can be considered as a proposition. If the truth value is false, then it cannot be considered as a proposition. So concern here is not just a fixed truth value but a true truth value. So let's see how we can convert a propositional statement, or how we can actually say that a proposition statement is a proposition using quantifiers. So when I talk of the universal quantifier, which is denoted by this inverted A symbol, so that means if I am talking of some variable x. So I say for all x p of x. So what does this mean? When I say for all x p of x, that means for all values of x, for all the values of x from the domain. Now here I am using a new word, which is domain. What does domain mean? Domain means the range of values that a variable can have. The range of values in the universe that a variable can have. For example, if I say that the domain of the variable x is z, z stands for integers. So that means x can take the values from its domain of integers, that is starting from negative numbers including 0 to all the positive numbers or natural numbers. So that is the domain of x in that case. So in that case, so this is what you mean by a domain, and a domain is always represented by a capital U symbol. So capital U here means we are talking of the domain. So for all x, or for the universal quantifier, when I want to prove whether a propositional statement is a proposition or not, in that case I write for all x p of x. So the moment I say for all x p of x, that means for all values of x, for all the values of x from the domain of x, p of x must have a truth value which is true. So that means for all the values of x from the domain of x, if p of x has a truth value true, only then you can consider p of x as a proposition. And if I talk of the existential quantifier, so the existential quantifier, as it is denoted by this symbol, it means for this I say there exists x such that p of x, or there exists an x p of x. So this means that for some values of x. Now please note the difference here. In the case of universal quantifier, I am saying all values, and in case of existential quantifier, I am saying some values. So here for some values of x, that again those values would be from the domain of x. So for some values of x from the domain of x, if p of x is true, then I can say that p of x is a proposition. So I hope by now you can clearly identify the difference between the universal quantifier and the existential quantifier. In case of universal quantifier, for all the values of x, px must have a truth value true. Even for a single value, if you have a truth value false, then px is not a proposition. And on the other side, for the existential quantifier, if for some values of x, p of x is having a truth value true, then p of x is a proposition. By some values, I mean even if for one value of x, p of x is true, and for rest all other values of x, p of x is false, even then you will say that px is a proposition. Now let us see this with an example. So first of all, we'll start with the universal quantifier. We'll see an example for the universal quantifier. Now if I say for all x, p of x, in that case, what does p of x represent? If I assume that p of x is representing x is greater than 0, and I give two domains for x. The first domain is integers and the second domain is positive integers. So when I talk of integers, integers include both positive and negative natural numbers including 0. So since this is a universal quantifier, so in that case, even if for one value of x, p of x is found to have a truth value false, then p of x cannot be considered as a proposition. So out of so many values, how will I find out whether it is a proposition or not? By taking a counter example. Now, as you know that integers also consist of negative numbers. So in this case, if I take a negative number minus 3, so minus 3 belongs to integers, then minus 3 is greater than 0? No. Minus 3 is not greater than 0. So the truth value of px for p minus 3 is false. That means this is not a proposition. Now, in the next case, the domain is positive integers. That means all the numbers started from 1 to 3 until infinity. So I'll take the lowest number. The lowest number here is 1. So we all know 1 is an integer. That means it belongs to the domain of positive integers. Again, 1 is greater than 0. Is it true or false? So it is true. So that means p of 1 is having a truth value true, and this is true for all the values of x. Hence I can say that in this case p of x is a proposition. Okay, now we will look at the existential quantifier and see an example for existential quantifiers. So in case of existential quantifiers, as we know, we say there exists an x such that p of x. So again we will take the same thing. Let us assume that p of x represents x is greater than 0. And we take two types of domains for x. So the first domain is integers. Again, integers will include both positive and negative numbers. So let us assume that we have taken a value as 7. Alright, so here what is the concern? Here the concern is that even if for one value of x it is having a truth value true, p of x is having a truth value true, then I can say it is a proposition. So here the concern is just to have one such value. Okay, so beyond that we can have any number of any such values for which p of x may be true, but we want to find out any one such value. So here we will take a positive number 7. Now we all know that 7 belongs to integers and 7 is greater than 0. So I can say p of 7 is having a truth value true. Hence p of x is a proposition. Then for the another case, we take the domain of negative integers. All right. So in this case, no negative integer can be greater than 0, that we know. So if I am taking an example of negative integers, let us I take minus 1. So is minus 1 greater than 0? No. So that means p of minus 1 will not have a truth value true. The truth value for this will be false, because minus 1, or for that matter any negative number, cannot be greater than 0. So the truth value for this is false. So for here we were concerned about any one such value which could give you a truth value for p of x, but here no such value can give a true truth value for p of x, because no negative number or no negative integer can be greater than 0. Hence in this case, for the existential quantifier, there does not exist any such x for which p of x can be true. Hence it is not a proposition in case B, but in case A it is a proposition. Now through a table we will see the difference between these two quantifiers. So we have the universal quantifier and the existential quantifier. So what is the difference? What are the major points of difference between these two? So first of all, universal quantifier means for all. That means for all values of x, proposition px must have a truth value true. And existential quantifier says there exists. That means even if for some or just one value of x, the value of px is true, then I say it is a proposition. Okay, so when is the universal quantifier considered to be true? It is considered true when p of x is true for every x in the domain. That means for all the possible values of x in the domain, the value of px is true, then only the universal quantifier is said to be true. And when is the existential quantifier considered to be true? When px is true for some x in the domain. That means not necessarily for all values of x from the domain, even if for some values of x, or for that matter, even if for just one value of x out of the domain of x, if px is true, then the existential quantifier is considered to be true. Okay, and when is the universal quantifier false? The universal quantifier is false when there is an x in the domain for which p of x is false. That means it says that even if for some values of x, or even if for just a single value of x from the domain of x, px or p of x is having a truth value false, then the universal quantifier is considered to be false. And when is the existential quantifier false? When there is when p of x is false for every x in the domain. That means when all the x from the domain of x, when all the values for x from the domain of x are having a truth value false, then the existential quantifier is considered to be false. So precisely I can say that for all x, p of x is such that the value of px1 and the value of px2 and till the domain, if the domain is having n number of values for x, then till p of xn, all these values must be having a truth value true. And for the existential quantifier, there exists an x for p of x such that from the values of x from the domain of x, if either px1 is true or px2 is true, or till the number of values in the domain P of xn is true, then the existential quantifier is considered to be true. So here for xn is the nth number from the domain. So n is the number of values, that means n is the number of total values for the variable x or for x in the domain.